There are two sheets over there. We have one last topic to cover. It's on the board. You need to understand and be able to explain a technology that uses electric fields, and I'm going to provide you with 3 of them. You also have over here a worksheet entitled Electric Fields All Types, because it basically covers, well, electric fields, all types of questions. That's the name. As always, on the back, answers, QR code, link to solutions. How many people were aware that there's a binder in here that has all the solutions in it? This binder says Physics 30S Solutions. Usually over there, but today it's right there. Okay? Always provided for you. Okay, so this really won't take too long. So at the end of today, you will have some time to practice Millikan problems, both ones that are suspended, as well as if you have any more video stuff to do, you'll have time for that as well. So I need your attention for about 20 minutes, so you need to put your phones away and give me your entire attention. I'm going to tell you 3 things. So these are applications of electrostatics, or if you want, electric fields. Let's begin. Figure 1 illustrates an office copier. You're probably familiar with a photocopier. The copying process is called xerography. It's technically called xerography. Right there. Well, that was not what I wanted to do. How come I can't see the tools here? I can't find it. Xerography. From the Greek word xeros and graphos, meaning dry writing. The heart of the machine is the xerographic drum, an aluminum cylinder coated with a layer of selenium. Aluminum is an excellent electrical conductor. Selenium, on the other hand, is what we call a photoconductor. It's an insulator in the dark, but becomes a conductor when exposed to light. And if you've ever used a photocopier, you know that when you press start, what happens right away? There's a bright light. Here's how it works. Consequently, if a positive charge is deposited on the selenium drum, the charge will remain there provided that the selenium is kept in the dark. If the drum is exposed to light, however, electrons from the aluminum pass through the conductive selenium and neutralize the positive charge. The photoconductive property of selenium lies at the core of the xerographic process. And here are the 5 steps right here, down below. And what I would suggest you do is you look at the pictures as I go through this paragraph right here. Here's the photocopier. Actually, here's what I'm going to do. I'm going to drag this over, put this up so that it's all on the screen at the same time. That might be better. Excellent. Okay. Figure 2 illustrates the 5 steps of the process. First of all, an electrode called a corotron gives the entire selenium surface a positive charge in the dark. That's what step number 1 is. Do you see on your diagram all those little positive right there? Yeah. Okay, there's this thing right here, this bar across the top is called the corotron, and the drum gets rotated around, and it creates a positive charge on that drum. Second, a series of lenses and mirrors focuses an image of a document onto the revolving drum. So here we have a big number 3. Teacher wants to photocopy a big number 3. The dark and light areas of the document produce corresponding areas on the drum. The dark areas retain their positive charge because when it's dark, it doesn't conduct electricity. But the light areas become conducting and lose their positive charge, ending up neutralized. So the big number 3, can you see how there's like a big number 3 being put onto the drum? But in a positive charge, Heather. Okay, is there an actual image you can see with your eyes on the drum? No, it's just there in positive charges. Thus, a positive charge image of the document remains on the selenium surface. In the 3rd step, right here, a special dry black powder called the toner is given a negative charge and then spread onto the drum. So the toner is put through an electric charge, it's given a negative charge, and then what does it do? because it's negative and the drum has a positive region, it's spread onto the drum where it adheres selectively to the positively charged areas. In other words, the negatively charged toner sticks to the positively charged image. Now what's on the drum? Big number 3, but in toner, stuck there because of negative positive attraction. The fourth step involves transferring the toner onto a blank piece of paper. However, the attraction of the positive charge image holds the toner to the drum. So the key is to transfer the toner. The paper is given a greater positive charge than that of the image with the aid of another charge. So the paper itself is actually charged positive. Lastly, the paper and adhering toner pass through heated pressure rollers. As a result of the heat, the toner melts into the fibers of the paper and produces the finished copy. So those last steps here, actually I'm going to go through the whole thing again one more time. So, positive charge image on the drum caused by the corotron, positive charge everywhere. Because of the light, some of the positive charge disappears, and what's left is a positive charge image. Then the negatively charged toner is then sort of sprayed or placed, spread around the drum, where it sticks to. What happens to all that leftover toner that doesn't stick, do you think? They pull it off and they recycle it. Exactly. Otherwise, it'd be a lot of waste, right? There is some waste. In fact, I was copying just yesterday, and it said that the waste toner receptacle was almost empty. Call the service department. So there must be some that is actually unused to be recycled. So, anyways, we now have a positive number 3 on the drum, and then when the negatively charged toner is stuck on the drum, then you get an actual number 3 on the drum in ink. Then they bring in the paper. The paper is given an even greater positive charge, which brings all that negative toner off. It's stuck in the paper. Then how do they make it stick on the paper? What do? They melt it. Which is why when the stuff comes out of the paper, comes out of the photocopier, it's nice and warm.
You just want to rub it on your face.
Nice and warm, like a nice blanket, right? Yeah, excellent. Okay, so this is an example of technology that uses electrostatics. Not so much an electric field, but electrostatics. A little bit. A laser printer you might be familiar with, right? A laser printer is used with computers to provide high-quality copies of text and graphics. The laser printer is very similar in operation to the xerographic machine, except the information to be reproduced is not on paper. Instead, the information originates in the computer's memory and is transferred to the printer through an electrical cable. Laser light is used to copy the information onto the selenium aluminum drum. So instead of this step right here with lenses and mirrors where you're actually sort of putting that image on the drum, it actually uses a laser that goes on and off many times a second and produces that positive image on there. That's how that works. And then what? Well, then it's exactly the same as the photocopier. So laser light is used to copy the information onto the selenium aluminum drum. A laser beam focused to a fine point is scanned rapidly from side to side across the rotating drum, as figure 3 indicates. When the light remains on, the positive charge in the drum is neutralized. As the laser beam moves, the computer turns the beam off at the right moment during each scan to produce the desired positive charge image, which in this case is the letter A, and then it's exactly the same as the photocopier. Figure 4 shows the general mechanism that turns the laser beam off and on as it scans across the xerographic drum. The light from the laser is sent through a device called a modulator. The modulator also receives the information to be printed from the computer and accordingly either allows the light to pass or blocks it. Thus, the laser output beam from the modulator is turned off and on at rates often exceeding 1 million times per second. The output beam is then directed by a series of mirrors and lenses to a rotating polygonal mirror that causes the reflected beam to sweep from side to side. When the beam reflected from the rotating mirror is directed onto the xerographic drum, the beam scans across the drum and produces the positive charge image. In other words, it uses magic. New photocopiers actually don't do this. This has become a quite old textbook. New photocopiers actually don't do this. What they actually do is they're a combination of laser printer and scanner. They scan it, you put the paper to be photocopied in there, it scans it into a picture and then is actually laser printed onto the paper. It works a little bit better. It means there's less moving parts. Okay, the one that you're probably most familiar with is an inkjet printer. Who has an inkjet printer at home? Lots of people. I have one. I finally got rid of it because I got tired of the ink always drying out. I wouldn't buy a laser printer. They're cheap. Anyways, an inkjet printer is probably the best one that shows how electric fields are used. So an inkjet printer is another type of printer that uses electric charges in its operation. While shuttling back and forth across the paper, the inkjet printhead ejects a thin stream of ink. Figure 5 illustrates the elements of one type of printhead. The ink is forced out of a small nozzle and breaks up into extremely small droplets whose diameters are less than 4/1000th of an inch. That's pretty tiny. Typically, about 150,000 droplets leave the nozzle each second and travel with a speed of about 40 miles an hour toward the paper. During their flight, the droplets pass through two electrical components, a charging electrode and deflection plates, and I will show you those right away here. Okay? Here's the charging electrode right here. Here's the deflection plates. So you would have like positive here, and you'd have like negative here. And inside those plates, you would have a electric field.
Ooh, I said that.
An electric field. When the printhead moves over regions of paper that are not to be inked, the charging electrode is left on and gives the ink droplets a net charge. So the charging electrode goes on, and now these guys coming out here have a positive charge. And when they enter the electric field, what happens? They are forced down and not on the paper. They're forced away from the paper. And they end up down here in a big reservoir. Whenever the deflection plates divert the charged droplets into a gutter and thus prevent them from reaching the paper. They are usually recycled because otherwise you'd be wasting a lot of ink again. Whenever ink is to be placed on the paper, the charging control responding to the computer turns off the charging electrode. Then what happens? It goes straight on through. How come? Because they have no charge. So they just go blaze it on through and land on the paper. The uncharged droplets fly straight through the deflection plates and strike the paper. Inkjet printers are popular because they can produce colored copies. Full color printheads use at least 3 nozzles for 3 different colors, usually cyan or blue, magenta, and yellow. Often they also use a 4th nozzle for black ink, and that's one of the downfalls of them is that you're always replacing the black ink, right? It's a pain in the butt. That's why I got rid of mine. By adjusting the amount of ink that each nozzle produces, the printhead can deposit any color on the paper. So there's actually 4 heads, right? And they're all firing these things through. And depending on whether they're charged or not, right, that ink is thrown back in here and recycled. Pretty complicated stuff, right? And yet they charge you like 75 bucks for it. It's pretty cheap, really. Once they figured out how to do it, to actually produce it, it's pretty cheap. Okay, that's all I really have to say on that. I will tell you this, though. I will select randomly one of those 3 topics, and you have to give me sort of a 3 or 4 mark explanation on the test. How one of those 3 things works.
Pick the last one.
I usually do this.
Yeah, there's 3. How are you going to flip a coin and something at 3?
Maybe I could do that.
Well, you have to memorize all 3 of them.
No, you don't. You got a cheat sheet.
Do you have a 3-sided coin, Mr. Bender?
Yes, I do. I'm a wizard. Okay, that's all that I have. Today's Wednesday, right?
You're a wizard, you're not teaching at Hogwarts.
In fact, why am I teaching it all? Test is Monday, right? You got 2 days, and you got half of today. My goodness. There is no excuse for not knowing what's going on in this unit. What you ask is in this unit, Mr. Bennett. Oh, it would sure be nice if we had an outline of some type. You know, like the one that I gave you already. That's also posted to Schoology. Let's just go through this and see if we've covered everything. Have I defined the electric field qualitatively as the region of space around a charge where a positive test charge experiences a force? Indeed I have. Yeah, you did. Have I diagrammed electric fields using lines of force with respect to a positive test charge, including single point charges, near two-leg charges, and blah, 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 blah? Indeed I did. That's when I did this stuff. Remember that day when I was drawing pictures and you were too? Did I define the electric field quantitatively as a force per unit charge? Yeah, I remember saying that.
What do you say?
Did I give you E equals F over Q, and did we solve problems using F equals QE? Uh-huh. You all have this piece of paper. Who has it? Hold it up. Thank you. Gage has it. Oh, it's in your binder. Did we solve problems for the motion of charges between parallel plates where the net force is equal to FE plus FG? Yeah, that's what we did yesterday. And did I also do it when F net is equal to 0? Yep, that's when we had the charges suspended, right? Did you describe a simplified version of Millikan's experiment for the determination of the elementary charge? You did indeed, in your video. And did I define the elementary charge and convert between elementary charge and coulombs? You betcha I did. I covered it all.
This is the last year.
I should do some magnets.
What days are exam?
Your exam, that's a real good question. Let's see if I've got it listed on Schoology.
Say the 28th, please.
If I'm not mistaken, your exam is on the Thursday afternoon. Am I right? That was you guys, hockey guys were talking about that, right? Let me just see here. Yes, Thursday the 29th in the afternoon. It'll be in here. Let's put that on Schoology. You might want to put it on in your phone calendar. Add event. '29th. Not 1 a.m.
Is that a test or 1 a.m.?
No.
I'll come here and we'll do it in the morning.
101.
What's 101?
Yeah, well, that's for people that show up late.
Yeah, we have like 12 hours. Is it right that we have 12 hours to do it?
I will RSVP so you can, say you're coming.
What's that stand for?
What does it stand for? Oh. Response, s'il vous plaît. No, that's what it means.
And what does that mean in English? Yeah.
RSVP.
You're going to look it up.
I'm going to show you that I'm right. Because really, could I be wrong?
Online dating.
Yeah, that's what I'm going to click on. In the context of social limitations, RSVP is a request for a response from the invited person or people. It is an initialism derived from the French phrase "Répondez s'il vous plaît," literally "reply if you please," or "reply please."
Say that.
I did.
French code. Why did you do that?
I don't know. It's just culture. Why am I so smart? Oh, you say that like it's a bad thing. It's good to be smart.